Hi, welcome back to another Webots and Erebus tutorial by Jeffrey Cheng and Victor Hu. This is tutorial number 5, and this is the first part of 2 videos where we introduce to you a navigation algorithm for traversing the maze. Now, there are multiple ways to go about navigating the maze. For example, you could do the thing where you follow the right-hand wall, or you could generate your own pattern of movement to go around the maze. The problem with these is they don't guarantee that you navigate the entire maze by the time your timer runs out. In the algorithm that we propose to you in these 2 videos, it will guarantee to you that you will traverse the entire maze by the time your 8 minutes runs out. So if you don't really have a good idea where to start, go ahead and watch these videos, and this will give you a good algorithm as to how to navigate the maze. By no means do you have to use our algorithm, nor is it the best out there. However, it is a good starting spot for tackling the Erebus competition. So in this video, we're going to talk about mapping. Mapping is just the robot writing information that it learns about the maze to some sort of map, just like mapping is in real life. Except in this situation, the robot is going to be moving around the maze, and as it learns stuff like the wall arrangement, it's going to write that information to some kind of map. That way, when our robot needs to navigate over places that it has already been, which is pretty much guaranteed within a run, the algorithm can access the map, and it already knows the arrangement of the walls in that territory. And we really need mapping for 2 main reasons. Firstly, we need the robot to remember where it has been and where it hasn't been. That way, we guarantee that the robot explores the entire maze. If you're doing something like wall tracing, the robot is going to follow the right-hand wall, but it doesn't guarantee you that the robot navigates the entire maze, especially the inner parts of some of the rooms. So you might miss out on some of the victims that are in the middle of the room. If you do something like a random pattern of movement, that also doesn't guarantee you that you navigate the entire maze. You might miss out on some victims. If you use mapping, however, you know where the robot has been and where the robot hasn't been. As a result, you can always get your algorithm to get the robot to find a path to some place that you haven't been, so you always guarantee you that you explored the entire maze. The second main reason we need mapping is we need to store the wall arrangements. Now, we always want to navigate the maze as efficiently as possible, so we make sure that we don't run out of time. Now, if we make these random movements, there's no guarantee about how good our path is. It could take some extremely long path or some extremely bad path to some areas of the maze. If we use mapping, however, let's say our robot needs to get from where it is to some section of the maze that it has not been before. If we have a map, our algorithm can use the map and the wall arrangements stored in that map. It can find out the most efficient way to get to that unvisited section of the maze. As a result, we have a nice efficient navigation of the maze. So these are the 2 main reasons why we need to map the maze. So now we got to figure out the design behind our map. And our map really needs to do 2 things for us. First off, it needs to remember where the robot has been and where the robot has not been. That way our algorithm can figure out where the robot needs to go to the unvisited sections of the maze. It also needs to store the wall arrangements of the maze. This is so our algorithm, when it goes to move to the unvisited places in the maze, it can access the map and use the already seen wall arrangements and figure out the best path that it can take to get to the unvisited sections of the maze. Well, the question is, how do we really do that? We can actually start off by dividing our maze into a bunch of grids. And each grid in front of you, we're going to refer to it as a section or tile of the maze. So this right here is a section of the maze. This is another section of the maze, and these are also tiles. Section and tile, for our purposes, are basically going to be synonymous. And basically how our map works is it's just going to be a collection of all these tiles of the maze. So our map has to be some data structure that can hold a bunch of elements where each element corresponds with a section of the maze. So one element of the map would be responsible for storing information about this section, such as wall arrangement and have I been to this section. And then another element of the map would be responsible for this section, and another element would be responsible for this section, and etc. How it's basically going to work is my robot starts off in this section right here, because it's basically inside this one, and then it's going to access the map and it's going to store information about this particular section. So it's going to use its distance sensors and it's going to observe that there's no walls in this section at all. And then since I've been to this section, it also needs to write that down. So it would go to the map and find the corresponding element that corresponds with this particular section, and it's going to write down inside that particular element, hey, there's no walls and I have been here. Then it's going to move from this section into this section, and then once again it's going to access the specific element for this particular section of the map, and then it's going to write down, hey, there's no walls, and then I have been here. And then like this, that's how the robot navigates around the maze and starts filling out information. And you might realize that, hey, at the beginning I'm going to have no information written in my map. That's perfectly fine, because if our robot keeps only to tiles that it's visited in order to get to tiles that it has not visited, we only need to store information about the tiles we have visited. So right here, even though we don't know anything about the entire rest of the maze, we do know that, hey, there's no walls here, so I can go in any direction that I want. And then as it moves around the maze, more and more information is written about the map. So then, if I take this grid of the maze and I simplify and put it on a little smaller scale, it'll look something like this. Now, since this grid is obviously smaller than the one in the previous slide, in real life, this would be my map, so it would have to be the same number of grids as the one in before. But this is smaller, but it still illustrates the same concept, because this looks exactly like a two-dimensional array, where each element of the array corresponds to a specific section of the maze. And also, I can actually number the elements like this, and as you can see, it forms a contiguous series of numbered tiles. That means I can actually put this in a one-dimensional array form. So there are actually two ways I can go about implementing my map. I can use a two-dimensional array or a one-dimensional array. It really does not matter. There's slight differences between the two, but just work with whatever you're more comfortable with. So then, this structure is perfect for representing the maze how I want it. Each element of my array corresponds to a specific section of the maze. Then, if I want to write information about a specific section of the maze, I just have to edit a particular element of my array. As you can see, if I want to write about section 0 of the maze, which is the top left-hand section, I would just have to write about element 0, change the value that is stored in element 0. If I want to write information about section 1, which is the section to the right of section 0, I just have to modify element number 1 in our array. And as you can see, each element of our array corresponds to a section of the maze. So when you go to write information about a particular section of the maze, all I have to do is modify the value inside the corresponding element of the array. Now that we have the general structure of our maze outlined right in front of us, let's get a little more detailed. So as I said before, each one of these grids represents a tile, such that you can see that arrow points to tile number 8, or section number 8. And let's recall our snapshot of the maze before. This is a zoomed in version of the overall maze we had in the previous slide. I'm going to add in some grids, and remember that once again this is a zoomed in image of a grid, and we're actually going to focus on just the middle tile, so that one right there. Now this is a tile, and each tile has information, and we call those attributes. And these attributes pretty much consist of where are the walls and have I visited before. These are pretty much the only attributes that we're going to need so far. You can always add in anything that you want, but these are the very basic attributes. So each tile is going to have these attributes attributed to it. Makes sense because each tile is going to have its own wall arrangement, and then each tile is going to have its own boolean of whether or not we have visited it. So in our maze, it's just going to be an array, one-dimensional or two-dimensional, of a bunch of elements, where each element is a tile that stores information about its walls and has it been visited before. Now, for actual implementation, each tile of the maze is going to be represented by one byte, which is 8 bits. And each bit of that byte is going to represent information about the maze. Let me show you what I mean. So right here we have a byte, an empty byte set to all zeros of 8 bits. Then we can use each bit to convey a certain amount of information about the tile. For example, the rightmost bit is going to be off if there's no wall to the north. It's going to be on if there is a wall to the north. Then to the bit to the left, that represents the east wall. So once again, it's going to be off if there's no wall to the east, and on if there is a wall to the east. And as you can see, we have bits for also the south wall and the west wall. And therefore, using these 4 bits, we can store the wall orientation of each tile. So if we go back to section 8, you will recall that it had a wall to the north, right here, wall to the west, right here, wall to the south, right here. But there was no wall to the east. So that means the north, south, and west bits are going to be set to 1. So the north bit right here, the south bit right here, and the west bit right here are all going to be 1, while the east is 0. And that's how we write information to our map. And then when we go on to read it, all we have to do is check if that bit is set to on or off to see if there's a wall there. Then, as we said before, the visited, whether the tile has been visited or not, it just requires a boolean on or off, so that gets 1 bit by itself. So 0 for not visited, and 1 for it has been visited. So now that we have the basic outline of our map, we also need 2 extra variables to keep track of where we are and what direction we're facing. And that is the section variable and the orientation variable. So these are both going to be global variables that are accessible throughout your entire program. And they're very simple. The section just stores which number section that you are in. So let's say you are in section 7 right here. The section variable will simply store the number 7, and that way you know where you are, and from there you know in what direction to proceed. Then we're going to have an orientation variable, and that's just going to store north, east, south, west. Now you can't actually store the directions, but there are multiple ways you can go about setting it. You could define numbers, use macros. You could use enumerations, which is what Victor and I did, and there are other ways to do it. It's completely up to you. But the point of it is this orientation variable is going to store what direction that our robot is facing, so that it knows what walls to check and in what direction. So to summarize the concepts behind our map, let's recall our sample maze from before. We're going to divide this sample maze into a bunch of grids, where each grid is going to represent a section or tile of the maze. We can then visualize this as a 2-dimensional array, where each element of the array is a section of the maze. So element 0 of our array is going to be section 0 of the maze, and same thing with element 1 and section 1, and etc. So this structure right over here, this array, 1-dimensional or 2-dimensional, is going to be our map. Then each element of our array, as I said before, is a tile. Let's say element 23 is section 23 in this orange box right here. We're going to have to store information about tile number 23. And in doing so, we're going to use 1 byte to represent the information. So to access the information of tile 23, we're going to index an element of our map. And that element is going to be this byte right over here. And the first 5 bits are going to be attributed to 5 different pieces of information. North wall, east wall, south wall, west wall, or have I visited it or not. Then, to keep track of where we are in the maze and what direction we're facing, we're going to use the section and orientation variable. So to give you a real scenario of something that might happen while you're running in the maze, let's say I have a robot that is in section number 23 right here, and it's facing up. Well, let's fill out our information accordingly. So we know that we're in section 23, and we also know that we're facing north. Then we're going to have to fill out the information of element 23. So we're going to access element 23 of our map array, and then we're going to fill out the byte that is there. We're going to fill out a north wall because there's a wall to the north, a south wall, and a west wall. And since we're already in this tile, we're going to mark it as visited by setting a 1 here. So while the robot is in this element, it would use the distance sensors in the code, and then it would fill out this byte, which is an element of our map array, accordingly.
To store information for mapping, we're going to use a custom data structure that represents information for one grid tile. So to do that, we're going to be using something that you'll find in C or C++. You might have used it before. It's called a struct. And structs are essentially custom types that we create ourselves that can store multiple variables within them. So for a single grid tile, we can create a tile struct that stores information about any of the walls along the north, east, south, or west side of the tile. And this kind of grouping will be very useful later on for a navigation algorithm. But for right now, we're also going to have an additional variable to store whether the tile has been visited by the robot or not, which is also very important for navigation. So to create a struct, all we do is type def struct. And we're going to have a bool for viz. And this is going to store whether it has been visited by the robot or not. Bool north, east, south, and west. So we essentially want to store the state of the tile, and that can be true or false. Like, for instance, true if there's a wall to the north, false if there's no wall, and so on for every direction. And true if we visited this tile before, or false if we have not. And the reason why, you'll notice I'm using some kind of special syntax with these colons and ones. Instead of storing these as individual booleans, this is actually something called a bit field. And what that means is that each of these variables, viz, north, east, south, and west, actually take up 1 bit. And that's useful for conserving space. It's not too much of a concern right now since we're just using a simulator, but if you had like a physical real robot with limited memory, this might be something you want to consider, since you do have to store a lot of mapping information about all the grids in the entire world. Just to demonstrate how to use structs, we can define our own type down here. And essentially, we're going to call this tile with a capital T. And now we created our custom type called tile. And anytime we want to use it and creating our own tiles, we can just do something like this. Tile. So now we created a variable tile that is of our custom type, which contains northeast, southwest, and viz. And down here, you can just set the field of tile by doing tile.viz or something. And we could just set that equal to 1 or true. And we can also print it out like this. So it's very simple. You can just access whatever's within tile by having a period after the word tile. So at this point, you might be wondering, what is actually considered like a tile within the Erebus world? And truthfully, the answer is that this world isn't actually tile-based. You'll notice there's irregular walls all around, and nothing conforms to like a perfect tile shape. So we actually need to make our own artificial idea of what a tile is. And that depends on what you want. For us, we could just define a tile as being 1 meter in length, and that'd be perfectly fine. So I'm going to do that up here. Grid size to be 1.0, and that's going to be in meters. So what this is going to say is we're going to use this definition later on, and once we want to move forward a tile, for instance, then we know that that translates to 1 meter forward. Additionally, we need to define the size of how many tiles are we actually going to store. That's going to depend on the size of your world. Ideally, you never want to exceed, you never want the robot to exceed the indexing of how you store the tiles, because that would cause you to go out of bounds, and that's going to cause all sorts of errors. So your maximum tile should always be bigger than the world itself. So we should have, since this is a 1 meter tile size, then if we know the size of this entire grid, we can figure out how many tiles we actually need. And a good number for us would probably be around 35. And that's just a safe estimate. Of course, that depends once again on your grid size, because if you have more or a larger grid size, then you probably need a smaller amount of tiles. But if you have a smaller grid size, then you probably need more tiles. So 35 is a safe estimate. We're probably never going to go over that. We're going to create an array essentially to store the entire maze. And this array is going to be an array of tiles because the maze is comprised of tiles. There's two ways to generally go about this. You could either store it within a 2-dimensional array or a 1-dimensional array. A 2-dimensional array might be more intuitive at first because you think that the maze can be split into rows and columns you can easily index. We're actually going to go for a 1-dimensional maze for our tutorial though, because there's some benefits to 1-dimensional maze. For instance, you only actually have to keep track of one variable, and although it's less intuitive, you eventually will get the hang of it if you continue to use that. So we can create our maze array by doing tile, since the whole maze is comprised of tiles, maze, and since it's 1-dimensional, it's going to have to be the maze length times the maze width. And this is going to store information about the walls of the entire maze. So every time our robot moves into a new tile, we're going to use our ultrasonic sensors in order to detect whether there are walls surrounding our current tile. We're going to stick to the frontal 8 distance sensors like we've done in our previous tutorials, which means we can check north, east, west. But feel free to use all 16 if you want, so you can also check south. We've gone over how to use the ultrasonic sensors in the past, so we won't cover the code for how you get the readings from the sensor in this tutorial, but you can look back on our previous videos for that. Instead, we're going to talk about the process for how you translate the sensor data from the ultrasonic sensors and input it into your data structure. So imagine that our robot is facing north like it currently is. If we see a wall to the robot's right side, then we know that it's going to be east. But say that we're facing east. We have to know that if we see a wall on the robot's right, that's going to be south. And if we look at our enum up here, if you've ever used enums before, you might know that north, east, southwest, those all actually correspond to 0, 1, 2, and 3. So for instance, north is 0, east is 1, and so on. So if we're facing east facing east, for instance, and then we see a wall to the right, then that would normally be south. And in our code, this is going to be like pseudocode. We can say like, if we see a wall to the right of the robot, then set the tiles wall for the orientation plus 1 direction. Because if you imagine if our orientation is east currently, and then we see a wall to the right, then east plus 1 would be south. So we'd set true for the tile seeing a wall to the south. But that leads to a problem, however, once you get to west. If you're at west and then you want to set a wall north because you see a wall to the right of the robot, if you add 1, then you go outside of your enum. So this poses a problem. And same thing for north, and you see a wall to the south. You're already at 0. If you subtract 1, then you're going to go back to west, right? And the way we're going to fix that problem is we're going to do something that's more advanced. It's called using C++ operator overrides. And you won't have to do this if you're not comfortable with doing it, but it's something to make our lives easier. So a neat feature of C++ is that it actually allows you to override what its operators do. For instance, the plus sign is one operator in C++, and normally you can use it to do things like add numbers together or concatenate strings. But say we have a custom data structure like we made for tile, or we also have our enum here, orient. We can actually create a custom purpose for the plus sign. And you'll see that function right here, I pasted it in. It's an operator override function, and same thing for the minus sign. And just as an explanation, how this works, it's very specific to C++, and you'll see that the return is orient. It's the word operator followed by the type of operator, which in this case is a plus sign, and the two terms that we're adding together. In this case, an enum, and also a number, an integer. And we're going to return the orientation added by the number modded by 4. And what mod 4 does is it ensures that it's between 0 and 3. So for instance, if we were at west and we saw a wall to our right, then we would be doing 3 plus 1. And then this is the wall we're going to set as true because that would be the north wall. And since this goes out of bounds out of our enum, if we have our operator override, however, it's going to do a special check by modding 4. And since 4 mod 4 is 0, that's going to return 0. And essentially what we've done here is added a safe method where we can manipulate our orientation in order to get where our walls are going to be set or not. And same thing for the minus operator. We did the same exact thing. If we're facing north and we see a wall to our left, that would normally be the west. But since if we do 0 minus 1, we get -1, and once again, that's out of bounds out of our enum, we just have another check here where we mod 4, and we make sure it's going to be west. All right, so now that we've gone through all the concepts you need to know, we can finally move on to a demonstration. So this is just some code I wrote up, and I'm just going to walk you guys through it. So I have my section variable, which is storing the current tile I'm on. I'm just going to keep that in at 0. And orientation, we created an enum for that. And we have our operator overload methods down here. And you're going to see how we use that later on. Plus, we're going to create our 8 distance sensors. And now these two functions I just wrote, and I'm going to explain get surroundings first. So get surroundings, it's going to read in the wall data from the ultrasonic sensors for the north, east, and west walls. And it's just comprised of 3 if statements. The first if statement is for distance sensor 4. And if you remember, distance sensor 4 refers to the frontal distance sensor that's pointing straight ahead. And if that's greater than 500, and 500 is just an arbitrary number I set, so pretty much if it's just close enough to the wall, we're going to call set wall and pass in our orientation. And this set wall function, all it does is it's a switch statement that takes in our orientation and then sets the corresponding wall for the current tile. And for instance, case n, which is north, then we just set the north tile for the current, the north wall for the current tile to be true, or 1. Now back to get surroundings down here, the second if statement for distance sensor 0 is for the left direction. And we do the same thing, except this time we set wall orientation -1. And the reason why we do that is, if you'll remember, for instance, if we're facing east and we see a wall to our left, then that refers to the north wall. And we can just subtract 1 to go back to north. So we'd be setting the north wall on our left side to be true. And we do the same thing for the right side, which is distance sensor 7, except this time we add 1 instead of subtracting 1. So for instance, if our robot is orientated north and we see a wall straight up ahead, then we know we need to set a wall to the north. If we see a wall to the right, then we need to set a wall east. And if there's a wall to the left, then we need to set a wall for west. And this is where the operator overloads come in handy. So if you remember, we use the operator overloads to make sure we don't cross out of bounds of our enum. So if we're west already and we see a wall to the right, which would be north, then to make sure we don't go out of bounds, when we add 1, then this operator overload will automatically mod 4. So the operator overload essentially replaces the basic function of the plus sign. It replaces the meaning of the function plus sign to do this instead of just adding numbers like it normally would. All right, and then down here, this is what we've seen before. We just initialize our 8 ultrasonic sensors, and then I set my starting orientation to north. And just to prove to you guys that the walls are empty, I'm gonna print the value of the walls out in the beginning, and then in my loop, I'm gonna repeatedly get surroundings, and then after I get surroundings, I'm just gonna print out the values of all the walls. Okay, so one thing before the demonstration is that I had to change these arbitrary thresholds I'd set from 500 to something higher. So we have to get closer to the wall in order for it to count as a wall. And additionally up here in the operator overload for minus, I added 4. And that's just to make sure that the entire orientation is going to be positive. All right, so let me build that one more time. And if I run it, actually, let me restart. If I run that, so you'll notice that all of the walls are 0 currently. But if I manually move the robot closer to that wall, west becomes 1, which means that the robot sees a wall to the west. And same thing, now all the wall data is going to stay there, but if I move it towards the east, now there's an east wall. If I move it towards the north, there's going to be a north wall, and it's not going to make a difference if I move it backwards towards the south wall, because we're not checking for the south wall. All right, but if I were to change, for instance, this orientation to west, and I'm gonna pause the simulation, and if I build that, reset the world. Let's say I actually move the robot to the west. So let's say we're in the west position, like so. So what should happen is that even though our robot's facing west, it should update our struct correctly to reflect and take into account that we're facing west. And our operator overloads should make sure that nothing gets out of bounds. For instance, if we're west and we see a wall to the right, we normally add one, which would take us out of bounds. But with our operator overloads, that ensures us we go back to north, which is 0. So just to show that that works, I'm going to run this. And everything's 0 right now. If we move the robot more towards the west, then you'll notice that it still says the west wall is there, despite our robot having changed its orientation. And if we move the robot up here, then we see a north wall. And if we move the robot down here, then we see a south wall. So that's just to show that this operator overloading is actually helping us in some way to make sure that we're not going out of bounds. So in conclusion, this video was mainly for you guys to get familiar with mapping, which will be a very important part of next week when we cover the actual navigation algorithm. So I know this may seem like a bunch of bits and pieces right now. We're going to tie this all together in the next video. And we demonstrated how to map a single tile. Once we get our navigation algorithm going, then it's going to do mapping simultaneously while it navigates around the maze. So next week, once again, we'll cover our breadth first search algorithm, and we're going to implement it and show you guys how you can navigate within the world.